All right, so when we're designing beams for shear and moment, we need the beam dimensions, the centroid, we need the moment of inertia, but we also need to know the value of shear and moment along the beams. That's done with either shear and moment equations or diagrams. Okay, so shear and moment in beams causes internal stresses, and that's what you design stuff for when you design things, is the internal stresses. So what we're going to do is go inside the beams and try and find the internal shear and the internal moment. And hopefully you touched on this a bit in statics. I'm not sure if you did or not. And so we'll develop it a little bit more for this class. So these are the internal reactions to the external forces acting on a beam. The sign convention for shear and moment is shown below, okay? So what we have here, what shear does is it's like a force inside a beam that's causing a shearing action. You know, we've gone over shear earlier in the class. The moment, it bends the beam, okay? So normally speaking, what we do is we start on the left and work on a beam and kind of start analyzing it and working our way to the right, kind of like we read left to right. So we're going to cut the beam and show these internal forces on the beam. Now the positive sense of these is that positive moment curls the beam up. Okay, so positive moment as you're working left to right is actually counterclockwise, which is good because that matches our general moment sign convention. That curls the beam up. There's positive moment, okay? The silly way to remember that is that positive moment makes the beam smile, okay? Negative moment makes it frown. So probably not going to be able to forget that even if you want to, right? Because it's so okay. Now, the shear is kind of a funny one. Positive shear, as you work your way left to right, is actually positive down. It's kind of funny, but that's how it works. So we have to remember that. So what we're going to do then is we're going to start off with a beam. Okay, and I'm on page 750 is where I'm at. We're going to find the reactions on the beam. Then we're going to make a cut through the beam and then solve for these internal shear and moments. Okay, that's what we're going to do. Now, the first part of this is finding the reactions. So let's not take that for granted. I know everybody passed statics because you had to be in here. But let's kind of review this a little bit. It might have been a while, so let's kind of have a look at some just sample reaction problems, just to be sure that we're comfortable with all this. And these are on 760 and 762. And what I have are just examples that go through some of the common instances that we might deal with when we're doing reactions. So let's have a look at this. All right, that's called a simply supported beam. I've got two pin joints. If you remember the symbols that are used there, a triangle. Sometimes it'll have a little bit of a point on the top of it, a little dot there. But a triangle with those pins there, that's a pin joint. Now what that does is that causes reactions, right? Because what supports do is they prevent motion of certain types. And you look at the motion that's prevented, and that requires a force to prevent the motion. So that pin joint, it's grounded down below. You see the hatching there. That means a solid support of some type. That's not going to allow the object to move up or down. Okay, so what you would do then is put a force in there to represent that prevention of motion. Both of those pin joints have vertical reactions. Now, pin joints also do not allow motion left-right, and again, that requires a force to prevent the motion. So these would also have forces doing this, although, so what we would have here would be RCY and RCX and RA, Y and X. Okay. Now, however, we're going to kind of get a little bit more common sense than we might have in statics. That's what we would have done in statics. But I can tell the only applied force is down. So even though I've got RAX and RCX, they're going to be zero. They're not going to count for anything because I'm not applying any force in the X direction. So they're not going to do anything. So I can really focus more on RAY and RCY. All right? And I might even just call them RA and RC if I wanted to, because I know they only act in the Y direction. All right? Good? Now, we got that. Now, the strategy on these things is in statics, we've got three equations in two-dimensional statics. Because if the thing is not accelerating, we know that these conditions are met. Okay? Those three. Now, the moment can be taken about any point you want. Okay? Now, what you want to do in statics is look at the number of unknowns you've got for each equation. Sum of fx isn't going to get us much on this because there's nothing going on in the x direction. Sum of fy will get us two unknowns. Okay, but we only got one equation, so I'm probably not going to want to start with sum of fy. I'm probably going to want to start with a moment equation, because what I can do is get that down to one unknown. Where could you take moments about such that you would only have one unknown in your equation? Yeah, A or C, okay? Because a moment is a force times a distance. If you make the distance 0 by taking a moment about A, let's say, you don't have to worry about RAY. It won't enter into the moment, so you can solve for RCX. Okay, so that's the basic strategy on these. So how about finding RC or RCY, whatever you want to call it? We do that by taking a moment about A. So what's that going to be? So MA equals 0. And you can fill in the stuff here. What do we got? Okay. We want to measure all those moment arms from A. So what I do, I put the numbers inside of parentheses, then I attach the sign, because you can't really, I don't want to call that a negative 2,000. I just call it 2,000 times 6. Then I look at it and I go, okay, if I hold a pencil here out to the right and push down on it, that thing's going to rotate clockwise. So that's a clockwise moment. So what that means is that's negative. Okay? Put the numbers in the parentheses, I put the sign on the outside is how I do that. And then what do we got pushing back here to hold it in equilibrium? We got RC, and what's the moment arm on that? It's 8, yeah. So remember, you're coming from A. You're taking the moments about A, so 6 and 2 make 8. Okay. So 8 RC is equal to, is that 12,000? When we get that sorted out, so I can solve for RC, and I think that's going to be about 1,500, I think. Doing all right with that? You all remember this stuff? Okay. Now, the quickest way to solve the rest of it is go to a force equation. They're easier and faster, less apt to make errors on these. So I would probably go with a force equation next. So RA is 500 newtons. Okay. So that's basic statics right there. That's the approach. You got any questions on that? We're going to be doing a bit of this, so I just want to get you reoriented to it. Okay. There we go. All right. There's a distributed load there on the left. What are we going to do with that? What do you want to do with a distributed load before you start in on all the other stuff? Okay, with a distributed load, probably what we want to do is get it broken down into a single force and a location. Okay. Now the force is equal to the area of the distributed load. the location is at the centroid of the distributed load. That's a rectangle, so I'm going to end up with a force pushing down on the centroid of the rectangle. Now the force is equal to the area of what's called the load diagram, okay? And what is the area of the load diagram? What do we got? 5 kilonewtons per meter. That's the height. Times the base, 4 meters. Does that come out to be 20 kilonewtons? Is that about right? Okay. That's going to go there. Now we want to know where that is because we're going to take moments is what we're going to do. So we want to measure it here. Yeah, that's going to be 2 meters because for a rectangle, the centroid is equal to a distance of half the base over from one side or the other. That's how that goes for a rectangle, okay? So we're going to have that 20 kilonewtons times 2, and then once you finish it up and find RD and RA. No. 8 and 16 is what you're looking for. I'm not quite sure. Is that it? So 20 times 2, which would be negative clockwise, 4 times 6, which would be negative clockwise, plus 8 RD, so 8 RD's 8. And then RA up, 20 down, 4 down, 8 back up, RA 16. So those are the reactions. Okay. Good with that one? How about that? Why don't you find the reaction at C? Okay, it's going to put reactions on this thing. Now, this is a couple there. There's a big clue on a couple and how you handle it, and the big clue are the units. There's already a meter on there. That means there's already a moment arm on there. You don't need to add another moment arm because it'll mess your units up. Okay? That couple affects every point on that object with that amount of torque or torsion, or, well, it's not really torsion, but moment or whatever you want to say. Okay? So when you do your sum of MA equation, it's kind of deceptively simple on that. The moment's already in there. So that's just negative 3,000 Newton meters, negative because it's clockwise. Okay. But you don't put a moment arm on that. It's already got one. Okay. Y'all getting the reaction on the right there? Is it 600? Yeah, 600. Okay. We good with 600 there? So, and we're going to have plus, because it's going counterclockwise, 5 times whatever RC is. And what RC comes out to be then, 5 RC is equal to 3,000. So RC is 600 newtons. All right, so if that's 600 newtons, what's the reaction at A then? Yeah, the way to get that, the simplest way, once you got one force, is do a force equation. Do a sum of Fy and see what you come up with for RA. What do you do with that couple in the force equation? Not much, huh? Okay, the best model I can think of for a couple, especially for you mechanical engineers, just think of having a motor attached to that, having a shaft coming off, and that goes into a motor. And the motor's twisting it clockwise. The motor's not pushing the shaft up or down, it's just turning it, okay? It's just twisting it. So that's a couple, there's no associated force. So there's no force at all going on there. So what that's trying to do is spin that beam like a propeller clockwise. So to prevent that, RC has to push up on it with 600 newtons, and RA has to actually pull down on it with 600 newtons. Okay, so RA I didn't show in the proper direction there. So I got a negative sign on my answer. That means it's going that way, is what it's doing. The negative sign means my assumption was incorrect initially. It doesn't act up, it acts down. Okay? So the two funny things there with a couple is no moment arm because it's already got one, and it does not affect the force equation at all. It's just trying to spin something is all it's trying to do. Okay? You know, good with that? Yeah, they're kind of funny couples. They're simple once you get the idea, but you have to remember those two things seem to be the two important things, okay? All right. So with a couple, another way to think about it is a T-bar wrench, like a valve wrench, when you turn a valve, same sort of thing. You're just turning something. You're not pushing it up or down. Okay? All right, now the next page there, we got some more complicated ones. We've got a triangular loading for the next one. And we also have a cantilever support. Now a cantilever, probably the most common place you see that is if you take a beam and just push it through a wall. People make porches that way all the time. Second story porches, just take the floor joists for the second floor and just extend them out of the wall. Okay, very nice effect down below. You don't need any posts or support. You just got the thing just extended out into space. So what you end up having here for a cantilever is a Y reaction. Now, whether you need it or not, you have the potential for an X reaction. But the other thing you have in a cantilever that really makes the design of these, challenging, or you got to design big supports here sometimes, is you've got a couple reaction too. I'll call that MRA. Okay. So that's a reactive moment there. And see, we're going to have a load on account of this triangle kind of pushing down. What that's going to do is try and make the beam rotate, in this case clockwise, is what that's going to do. So you're going to have this thing like so, pushing down. Okay, and that's going to try and do that. And the support of the beam at the wall is going to say, no, you don't. You're not going clockwise. I'm going to come back the other way and prevent that, okay? So that's what's happening. So you get that reactive moment. So there's no fancy strategy for the solution process. You just go sum of fx, sum of fy, and sum of moments about A to solve. Now we've got a triangular load over there, don't we? So we got to know, the area of a triangle, of course, is base times height over 2, and then the centroid for a triangle is right there, and you're going to come a distance of not a half this time, but a third of the base from the right angle. And if you're going to the acute vertex there of the triangle, it's 2/3 of the base. Okay? So that's where the centroid's at, and then the area, as I was just saying, is the base times the height over 2. So that's how we handle a triangular load. We find the area of it, BH over 2, which is 1/2 base times height, because a triangle is half a rectangle, is what it is. And then once you've got that, you put that load right there, and then you locate it 1/3 of the distance from the right angle, or 2/3 of the distance from the vertex of the right triangle. Remember to add in the 2 offset there, and then we're going to get that figured up. 40-50 maybe for the load on that? I don't know. Maybe. I think 90, 900 times 4.4. Yeah, 40-50, we good with that? And then you want to know where that acts. Now, when you do that, you're getting 1/2 times 1800 newtons per meter times the base of 4.5 meters. That's where that comes from, and that's 4,050 newtons. Now notice the meters cancel, so the units work out there, okay? Now how far would that be from A? Let me get A, 5? Yeah, I think so. So what we're going to do to get this distance, we're going from A to B. And again, I like drawing my pictures because it just helps you. I'm going to go 2, and then I got to add in where I am on that triangle. Where I'm at with that triangle is I'm 2/3 of 4.5 over. All right. So that's going to get me 2 plus 3, that'll be 5, okay? So that's 5 meters. So I'm kind of simplifying my diagram here. I've got the reactions on the left, and then I take that triangular load and I just break it down to a load and a distance. So now I can do sum of Fx, sum of Fy, and the sum of Ma and find the reactions at the wall. See, once I know the reactions, I know all the forces acting on the object, and then I can figure out all the shears and moments inside of it, and then I can design it to withstand those things. So that's what's going on here. So we're doing all right with all that stuff? We got one more to do tomorrow. We'll do that. There we go. So sum of Fx is 0. It's Rax. Sum of Fy is Ray minus 4,050. So Ray is 4,050. And then the moment doesn't appear to be on there, does it? Oh, yeah, I've got the moment there. Sum of Ma on the top. So that'll be MRA, positive because it's counterclockwise, minus 4,050 times 5. So MRA is 20,250. So why don't we get a couple of these to do these moment of inertia problems. And these will be due on Monday, I think. So how about 322 and 323? And these will be due Monday. And is that the 3rd of March, I think? Yeah, that sounds about right, 1, 2, 3, yeah. So? What is it? Oh, they're 29? Oh, we got 29 days? Oh, okay. Thanks. Thanks. All right. So we're good with that. A couple of moment of inertia problems. So there you go. So, all right, I'll see you tomorrow. And, if you got any questions on that test stuff, let me know tomorrow. Okay.